Okay guys, so this video today is all about extrema on an interval. So we're going to talk about global extrema, we're going to talk about local extrema, and we're going to talk about how that applies to what we know in calculus so far. All right, so the first thing I want to talk about is the idea of what an extrema is. So when I hear the word extreme, you should think like something that's like over the top. So an extrema in mathematics really just means a maximum or a minimum. So whenever I think of an extrema, really an extrema is the same thing as a max or min. So it's kind of like the generic way of saying maximum or minimum. So here are two examples I want to talk about to distinguish what is a local versus what is a global extrema. First statement, Jack is the cutest dog in the world. What I would say about that statement is that would mean that Jack is the global extrema. What it means is that out of all dogs, out of the domain of all dogs in the entire world, Jack is obviously the cutest dog. The second statement I want to make is that Jack is the cutest dog on the block. So this statement's a little bit different. What it means is the domain is every dog that's like on my street. So out of every dog on my street, Jack happens to be the cutest. So it doesn't mean that he's the cutest dog in the world. It just means he's the cutest dog on the block. Thankfully for us, both of those statements are true. But that is the difference between what is a local and a global extrema. Local means that it's pretty much only true on a smaller open interval, while a global extrema means that it's true for the entire interval or for an entire closed interval. So let's go ahead and do some practice. Real quick, these are just the mathematical definitions for them. We're going to actually just talk about what they mean practically. So before we start that, though, I want to talk about these things called critical points. Critical points are going to be pretty critical for you to have success in the class in the next couple of months. Let me tell you why. The reason we call them critical points is they are where the derivative is either equal to 0 or undefined. So real quick, I'm going to draw a graph, and we'll talk about why that is so important. So here's my graph here. If I want to figure out, hey, where does the derivative equal 0? Out of all of these points, where does the derivative equal 0? What I'm looking for is where is the tangent line horizontal? Well, let's see. Let's go ahead and see where this tangent line is horizontal. I have a straight line for a tangent line here. Let's see. I have a tangent line that looks like this. I have a tangent line that, I have a horizontal tangent line right here. Okay. Let me actually make that look a little bit nicer. So I have a horizontal tangent line right here. And in fact, I have another horizontal tangent line here. So hopefully we're noticing that when the derivative is equal to 0, there is a big old chance that I'm going to have a maximum or minimum. So let me kind of make this statement for you. When you have a max or minimum, the derivative is always 0 or undefined there. But not every time that the derivative is 0 or undefined do we have a max or min. So it doesn't go backwards. It doesn't have an if and only if kind of statement to it. So the reason these are important is basically relative extrema can, but they don't necessarily have to happen where the derivative is equal to 0 or it's undefined. But anytime I do have a relative max or min, the derivative is 0 or it is undefined. All right. In fact, let's go ahead and let's practice this. So I've already kind of filled these out for you, so I'm just going to kind of talk through them. So first thing, determining key values of a graph. So when I talk about local extrema are like the things that are relatively like maxes and mins where the derivative still equals 0, such as like A and B. The absolute or global max or min is going to be like the tallest possible value I have. So in this case, the tallest value I have is C. And what's interesting here is the lowest possible value I have is D, even though D, technically the derivative doesn't equal 0 and the derivative is not undefined. The reason that D is an absolute global max is actually because it's an endpoint. So not every endpoint is going to be a global max or min, but endpoints are important to check when you're looking for global maxes and mins. I actually call them honorary critical points. Now, they're not necessarily critical points, but they're things that you should check because there is a chance that they are going to yield a max or a min. Critical values. So once again, this definition is going to come up all year. F prime is 0 or F prime doesn't exist. That is the definition of a critical value. So where is my slope 0 and where does my slope not exist? That happens at A, it happens at B, and it happens at C. Okay, let's move on to the next question. All right, so this question is pretty darn similar. Local relative maxes and mins. I have a local min at D. I have a relative max at A and E. I cross C off because C is actually a global max because it's the tallest. I have a global min at B because it is the shortest. Critical values. I want to know where is the derivative, where does the slope equal 0, and where is the slope undefined? Well, the slope is equal to 0. The slope is equal to 0 here at C, and I actually know that the slope is going to be undefined at B and at D. So the slope is going to be undefined at B and at D. The reason the slope is undefined at B and D is because a cusp happens there. So if we remember back to our limit days, if I try to take the limit of the slope from the left, I get a slope of what looks like -1. And when I take the limit of the slope from the right, I get a slope of 1. Well, the limit from the right doesn't equal the limit from the left, and thus the whole limit doesn't exist. And so we can say the slope at a cusp does not exist. So anytime we have a sharp turn in our graph, we can say the derivative there does not exist, and thus it must be a critical value. Okay, we're going to skip this one. All right, let's go ahead. I'm actually going to start this one over. Let's write it as it is. So my question here is, do I have a maximum, an absolute maximum, and an absolute minimum on this open interval? Well, looking at it, it's kind of difficult to find one because I would think that A would be a minimum and B would be a maximum. But A and B don't actually exist in this definition, in this graph. And so what I could say here is that because I'm on a closed interval, because I'm on an open interval, I actually don't have, in this case, I don't have a min and I don't have a max. I don't have a max and I don't have a min. And it has to do with this interval being open. If I were to close this interval, it's pretty obvious that the lowest possible point, the absolute min, would be A, and that the absolute max would be B. In fact, if I'm given any closed interval at all, I have to have an absolute max and an absolute min, and that is what is called the extreme value theorem. So the extreme value theorem says that functions that are continuous, so continuous means that I'm not going to pick my pencil up when I graph it. So there are no jumps and there are no asymptotes in the graph. So like this function here is not continuous because it has an asymptote. I'd pick my pencil up to get from one side to the other. In fact, I'd never even get to pick my pencil up because it goes up infinitely. This function here is not continuous because I have a hole. We could also say that this function here is not continuous because I have a jump. So provided the function is continuous on a closed interval, emphasis here on it being closed, I am guaranteed that there is a biggest value and there is a smallest value. In essence, there is going to be an absolute maximum and an absolute minimum. So if the function's continuous and it's on a closed interval, I will have a maximum or minimum. All right, so looking at this example here, the question is the function continuous? No, the reason it's not continuous is I have an asymptote. And so that is not going to be continuous. Next question, does the function have an absolute max on 0 to 6? Just looking at the graph, no. Just because the function is continuous and on a closed interval, I'm not guaranteed a max or min, but a max or min could still happen. In this case, no, because I'm going down to infinity and I'm also going up to infinity. So I'm going down to negative infinity and I'm going up to positive infinity. There's no way I have a max or a min. All right, after that, is this function continuous? No, it's not on the closed interval because I have a hole. I have a hole at 0 and I have a hole at 6. So just looking at this graph, we already talked about this question, there is no max and there is no min. This question, is the function continuous on 0 to 6? No, once again, I have an asymptote, so it's not continuous. So does the function have a maximum? Well, it can't have a maximum because this function is going up towards infinity. It's going up towards infinity. Does the function have a minimum? Well, it looks like the function is going down towards something, but there is no set point when the function is going to equal, say, for example, this is what's called a horizontal asymptote. It's getting infinitely close to 0, but it's never going to touch 0. So once again, I'm approaching 0. So the limit as x approaches infinity of whatever this function is 0, but I don't know exactly when that point is. And so I'm going to say no max or min here. For this question here, is the function continuous between 0 and 6? No, there is a hole at 4, but that doesn't necessarily mean there's not an absolute max or min. It's just not guaranteed. So the function have a maximum. In this case, we actually do. It happens at x equals 0 when I have a height of 4. But the next question, does the function have an absolute minimum? In this case, no, it doesn't, because there is a hole at 4, and that would be my lowest possible value. So we would say no, this function does not have a minimum. All right. So the next question, it says, okay, I want to graph something that has a max at 2, a min at 4, and continuous everywhere but 0. So what I drew, and this is just kind of an exercise, is I have a hole at 0, I have a maximum at 4, and I have a minimum I have a maximum at 2, and I have a minimum at 4. So just be prepared to be able to graph something given properties with maximums and minimums. You won't have to do that too much, but I thought I'd give you the example. All right. So for this last question here, in fact, I kind of just want to kind of talk through this one a little bit before I cross everything off. Question is, which of these functions must have an absolute maximum on the closed interval -3 to 3? So what we're going to use is we're actually going to use the extreme value theorem. Extreme value theorem says as long as I'm continuous and I'm on a closed interval, there must be a max and there must be a min absolutely. Well, one of the criteria is already met. I'm already on a closed interval, so the only thing I'm looking for is the function continuous? Do I ever pick my pencil up? Are there any asymptotes? Are there any holes? Well, looking at this one, letter B, if we go back to our pre-calc days, I do believe I made you guys memorize this graph. The graph of tangent has an asymptote. The question is, does the graph of tangent have an asymptote between -3 and 3? It does. It has an asymptote at pi over 2, and it has it at -pi over 2. So this one's not continuous. I'm going to take it off my list. Letter C, 1 over x squared. Well, if I were to graph 1 over x squared, it would have an asymptote whenever the denominator equals 0. Well, the denominator equals 0 at x equals 0, which is on my interval, so it can't be continuous. Same thing for letter D, sine of 1 over x. When x is 0, I get something that is undefined, and thus it's also not continuous. The only function that is continuous on the closed interval is cosine, and so cosine is going to be the one with an absolute maximum. All right, that's really all that I have for you guys today. We're going to continue to work with this. Next time we meet, we're going to talk about how can I determine extrema algebraically, how can I determine it using a graph, and how can I determine it using a table. Okay, I hope you guys have an awesome weekend.